Hey, Melissa,
Hey, Jam.
remember how we a while ago did some episodes about silicone?
I do, yeah. That was like 2 years ago.
Yeah. We have some questions from people about silicone and about mosquitoes and about mascara.
Okay, let's get into it.
Let's do it.
Hey, I'm Melissa,
I'm Jam,
and I'm a chemist,
and I'm not.
and welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Bonus.
Ask
Right.
a chemist edition.
We used to call it bonus, and I've just never been able to change it in my mind.
I know. It is a bonus edition, so you're not wrong.
It is, yeah. But Ask
Yeah.
a Chemist sounds more fun for sure.
Mm-hmm. And that's literally what's happening. You are asking a chemist. All those times we tell you to send your questions to us. If it doesn't end up being an episode, it ends up here.
That's right.
So
If it doesn't get lost in the inboxes.
that's right. Yep, that's true. Which we try our best at.
Yeah.
But
It's true. I really do try my best.
mm-hmm. Okay.
Okay, what questions do you have for me?
So these first ones are the two silicone ones. Would you prefer I ask you both of them in a row, or do you want to take them one at a time?
No, you can do them in a row. I saw these comments. These are on our YouTube channel. I saw these comments and I specifically wanted to talk about them.
Okay. So these are both, yes, like you said, both YouTube, both on our silicone one. We had two, didn't we, about silicone back then? Didn't we? Maybe.
Think. Hard to say.
Who knows? There's really no way of knowing. This first one, yeah. So you're reading together is what you said.
Yeah, I think so.
Siloxanes?
I think it's siloxanes.
Siloxanes are bad for the liver, but overall better than PFOAs, PTFEs, and BPA. That's just a comment someone just threw on there.
Yep.
This next one, separate comment. Heating silicone releases siloxanes into your food associated with liver and thyroid toxicity. Probably best to do your research properly before putting more inaccurate videos on the internet. Whoa.
Ow, owie, ouch, ouch, ouch. Okay, so to be fair, when I saw this, I was like, is that true? I'll go look it up. And it looks like there was a paper that was published recently, several papers that have come out since we published this silicone video in 2020, late 2024, 2025, and some in 2026, investigating siloxane, if that's how you pronounce it, chemistry. So, and one paper that I found about this basically said siloxane is just essentially silicone. It's another name for silicone. And just to kind of review, if you haven't listened to those episodes, I think it'd be worth it to go back and listen still. But most plastics are made of polymers, which are these small repeating units of the same atoms in the same order over and over again. We call it a large molecule made up of a lot of small molecules. But most plastics, Teflon, things like that, they're carbon-based. So the main backbone of that repeating unit over and over is carbon with maybe some like little functional groups on it, like little other groups of atoms. Silicone, not silicone. This is like a hard distinction audio wise, but silicone with an E at the end is made of a polymer that instead of having carbon in the backbone, silicon, the atom, has replaced the carbon atom. So you have traditional plastics are carbon-based primarily, and silicone is sort of like the silicon version of plastic. Okay, so that's what silicone is. And at the time, I found that silicone was found to leach significantly less, if at all, into food products, and that it seemed to be largely considered non-toxic. So I went and looked this up, and there was a paper that was released in 2025 specifically about baking with silicone in normal household conditions and whether or not it did leach chemicals, I guess, other than what the chemicals already make up the bread or whatever you're baking it in, into your food, because everything is a chemical. But does it leach specifically silicone polymer into the food?
Okay.
And what I found was, in this paper, what they found, I didn't do it, but what I found in reading this paper was, there is leaching of silicone into food. Siloxanes is essentially synonymous, based on what I was reading, with silicone, but there is leaching of some of those into the food when using, for example, silicone cupcake cups, like the things that you would bake in. So when you have silicone heated to high temperatures, it can leach initially. But what they also found was over repeated baking uses, the leaching was more minimal.
Okay.
So it seems like maybe the initial polymer formation of the silicone has some that aren't fully integrated into the silicone polymer or whatever the product is. And so that initial leaching happens when you heat it up and those sort of work their way out, but it lessens with repeated baking.
Huh.
And there is also some siloxanes that get into the air if it's high enough temperature as well. So there can be some leaching, but it seems, as I mentioned before, like it's probably not as bad as plastic still. It's minimal compared to that. And the other question is this even dangerous? And that is a harder question to answer because, well, there's not as many studies, that's hard. A lot of things we thought were fine initially ended up having more of an impact than we thought. But also, these polymers have a wide range. So I don't know why, but they are often referred to as like D3, D4, D5, whatever. And the D stands for the number, like that is for silicone. So silicon. So D3 would have like 3 silicon atoms in it. D4 would have 4 silicon atoms. So they found a range leached basically all the way from D3 up to D27. So you have like very small polymer, or like almost, would you even call it a polymer? It's so small, to pretty large that all could leach and could all impact us differently. But there was a pretty extensive test from the Canadian government that looked at D3 through D7 or 8, I think. I linked all this in our references so you could check it out. I saw it like pretty soon before we came to record today. So I'm kind of thinking of doing a more in detail episode coming up on this. But it seems like from my quick initial review that D3, which is one that they found, is actually a natural substance that's produced in plants. So people are like, oh, it's leaching these. But I feel like if you heard that it was leaching that from a plant, people somehow don't get as worried about that.
Yeah.
You know, so that's just something to think about. It seemed like D4 was a potential concern, but from what I saw that was published in the summer of 2025, they found that it could be detrimental to the environment, but there's not good evidence that it's detrimental to humans from what I saw. Now, there are earlier papers that did say, and I had trouble, I looked at the references and couldn't find this exactly in the references, but again, I was going pretty quickly. They said there was one paper that said D3 to D6 can potentially affect human health, targeting the liver through oral exposure, as well as the liver and lungs through inhalation exposure. So the key word there is they can potentially affect that. And they referenced this work from the Canadian government. Well, the Canadian government then did a deeper dive specifically on D4. And they found that D4, oh, hang on, I wrote it down right here. It was concluded that D4 was posing a risk to the environment, but not human health. Given that the previous regulatory activities for D4 can also pertain to and address mixtures containing D4, you kind of have to consider that too. So D4, I think, was the one that they were most worried about. D5 and D6 are found to not be a risk to environment or human health. So this is a pretty thorough investigation, and it doesn't seem like there's great evidence still that it's dangerous. That doesn't mean that we won't find out that it is. And so I guess I just wanted to acknowledge that there is updating evidence as we're going through, much like we did with the mosquitoes, as we're going through and years are passing, that maybe silicone is leaching some, but the evidence shows that it's still probably less. And we don't have compelling evidence that it's toxic. So if I had to pick between the two, that's still the one I'm probably going to go with. Using a, non-plastic material is also a great option. I have a friend from Sri Lanka, and she said they use natural materials to make everything. They I went to a restaurant with her, and they had all these spatulas and dishes, and she's like, this is what we actually eat off of, and it's all made from trees and whatever. And you're like, yeah, why do we have so much plastic anyway?
Right.
But anyway, so all that to say, there's emerging research. I wanted to comment on it. I didn't have time to go deeply in depth. We intentionally don't plan for that for bonus episodes, but essentially, there's some leaching, lessons over repeated baking, not a clear verdict on toxicity, but right now, it seems like they're not incredibly risky.
Okay.
But it's going to vary widely based on the chain length, and the smaller chains have been more thoroughly investigated, and there's been minimal investigation of the larger chains, and I don't think you can just put them all in a box. And there has been a trend in the United States for using some siloxanes in hairsprays and other cosmetic products. So it is something that we can look into, but especially through the skin, there is very minimal evidence that it's dangerous.
Okay.
But we always want to be learning more, right? Sometimes there is good evidence when people don't publish it because they don't want their business to go underwater, like some people that we know and have talked about.
Yes. Or it's the difficulty of you don't know what someone has not had time to research for a long time yet.
Right.
What we do know about plastics, has been building for a long time, people researching it. So it's sort of well, okay, we know more about it. Mm-hmm. Is it possible that we have the exact same situation with silicone over time? Maybe. But right now, the episodes we've done about both of them, one of them looks better. And of course, that's the whole business of looking for recent
right
stuff or whatever. But that's what's been so interesting about this. It's it really does, as for me as a layperson, remind you that it's all in progress.
Right.
Everything's all in progress. The the whole discipline of science, of chemistry, of all the way they all overlap in various ways, is that we're still figuring things out.
Yeah.
On a regular basis.
It's not finished yet.
It's a good thing.
Yeah.
So, interesting.
Yeah, and I will say the certainty with which these two comments, they kind of made me laugh because I'm like, well, we don't actually know either of those things. The first one said siloxanes are bad for the liver, but better than PFAS. I don't think that that's been researched enough for us to know if they are or not. Now, again, I couldn't find it, and I did it really quickly, but from what I remember back then and from what I was able to find this time, it didn't seem definitive in the 3 or 4 papers I looked at. It wasn't and they're terrible for this, it was there is a potential, people are suspicious, that kind of thing.
Yeah.
And the same thing with the other one. They release siloxanes that are associated with liver and thyroid toxicity. It's I didn't see great evidence for that. But I do try to do my research properly before I put in accurate information out. But anytime I do put in accurate information out, I will come on and offer a update and communicate the new information. But like Jim said, it's always in progress. So
yeah, but it's fun because it is also mean there's things to add on. The way that Melissa approaches all this stuff is this is the research she found at this time. It's like there's very little like, we don't have a vested interest in silicone over plastic or PFAS or any of these things. It's
Right.
nice not being beholden to any of these things. So if you're ever like, why did that get missed? Then send it to us. And it might even be that like, no, that is something that Melissa already saw and there's newer research. So that's why,
Right.
you never know.
Yeah. And I will say every person goes into any situation with their own like biases and tendencies towards believing one thing or another. But I try to gather all the information I have. I try to gather opposing viewpoints when it's something as controversial as PFAS or, things like that. And then I try to give a balanced view. And that's the best I can do. And then new information might come out, like a lot of the papers that came up were recent. So you also have to look at who's funding them and, are those people able to make plastic?
Yeah, right.
Is it, there's just like, or are those people that might have a vested interest in silicone succeeding? Oh, that's suspicious too. Like we need to look at those things also, so, and you might think like, oh, well, the government did it. They don't have a vested interest, but sometimes even government entities might have an interest, so, but the more voices you hear that seem like they would have minimal interest echoing the same thing with independent research, but coming to similar conclusions, the more confident I feel. But I would say that for me at this time, the majority of siloxane research indicates that it's considered low toxicity. Silicone's not considered to be high toxic, but I'm not saying that's what it's going to be forever.
Fair enough. Okay. Switching gears quite a bit because...
Wait, one more thing.
Oh, yeah. Sorry.
I think also it's likely that when I have more time to dedicate to this, I'll do a follow-up episode that's not like, oh, quickly on a July bonus episode, I'm going to mention this and we're going to move on. So
right.
I did a little more research than I normally do for the bonus episodes, but I just don't have the time built into my schedule to do a deep dive for a bonus. But it's not like, oh, I glanced and this is good enough for me. Likely we'll do a deeper dive relatively soon.
Switching gears, very different topic, but also one that we have had many episodes about. This is from Ash on Patreon. How do mosquito patches, wristbands, etc. work compared to general repellent? Sorry if you did mention this in the mosquito eps, but not sure that you covered patches and bands.
I don't remember that because that was years ago and also occurred over years.
Yes.
But here's what I do remember. So mosquitoes find us through a variety of ways. One is the carbon dioxide we emit. Another are the volatile organic compounds on our skin that are, they can be unique depending on if you're pregnant or not, if you've been drinking or not, if you've been exercising or not. There's like a whole variety of things that can change your volatile organic compounds, your carbon dioxide emission, your heat. All these things are like clues that that mosquitoes use to find people. And the way that many mosquito repellents work is by essentially masking your volatile organic compounds with a smell that mosquitoes don't like or don't associate with humans in a snack, right? So they're like, we're going to hide, it's like a smoke screen or an invisibility cloak. We're using something that is more, also I didn't say what volatile organic compounds are. Those are organic molecules that can easily evaporate and become airborne from your person. And there would be a higher concentration of them closer to you than further away from you. So mosquitoes will, follow that, likely increasing concentration, be attracted to that. And they're like, oh, this is whatever. And in one even more recent study, it seemed that people who had a higher concentration of eucalyptol, remember, were less likely to be attractive to mosquitoes. So all that to say, the way that many bug sprays work is by coating your body with that thing. It makes it to where your volatile organic compounds either aren't evaporating as quickly or they're not as noticeable to the mosquitoes as like, oh, this is a human, you know, this is the mixture of things that makes a human or a prey that I can find. So I think the way that patches and bands probably both work is they likely have something on them instead of it being on your skin that you have to spray, and it's working to do the same thing. I don't know that for sure. That's just my guess. Chemistry off the cuff. Is if I had to guess. I would also think they'd probably be less effective because of that, because they're not like coming into contact with more of your body. But if you're worried about there's good evidence that DEET is safe, not DDT though, but the DEET is like not super risky. But if you're someone who doesn't really want to mess with the unknown, it's relatively new discovery, fine. I accept that. I get it. I also don't like the way it feels on my skin, you know. It could offer some protection without having to go through all of the bug spray hassle, I would think, but it probably is going to be less effective. But that's my guess. And I wonder if you could do something similar to that by like getting your own wristband or something, hairspray, spray or a hair tie, and spraying it with DEET, like a bug spray, you know, and see if that works. I don't know.
Interesting.
But that's my guess. Do you have any thoughts on that? Have you used those with your family?
What's weird is that I do remember those when I was a kid. And so I have no idea what version that would have been, and like, are they similar to now, or have other ones today like different enough or whatever? So we have not used them. But as soon as I was reading the question from Ash, I was like, oh, wait, we did use those. And I don't have a strong memory if they worked well or not. I just, I remember it being like a thing living out in the country. And then we'd go outside, my parents would be like, oh, put one of those on. And yeah, just trying to, you know, evade the mosquitoes. But yeah, I'd be curious to look back at like, what was some of the like thoughts about what they were like back then in like the early 2000s, late 90s, and how do they perform now and that kind of stuff, basically. But that'd be cool. There's so many. Yeah, it's weird because as we've approached the topic several times, like there's so many, not just ways to approach like how it's masking us, but then also like the format of, is it a spray on us? Is it a the thing that's emitting something that's like you put on a table, you know, like a citronella candle or whatever, or is it something you're wearing? It's like there's so many form factors that make it hard for a lot of us to keep track of what is working well, what's good, and what are people able to research or whatever. But I should look into those. And also the idea of can we just genetically modify mosquitoes so they can't find us as well? Because they did that where they're like, oh, if you disable this gene or like this, I don't exactly remember. It was like there's something that they did in the mosquitoes themselves. They're like, if you block this gene, they have a much harder time. Yeah, that was a fun series. I like that one. Yeah, me too. Okay, ready for another gear shift? Yes. How does waterproof mascara work? This is from Ebony on Instagram. Okay, I just have a guess about this. Okay. I suspect that regular mascara that runs when you cry or whatever, whatever molecules that they're actually the pigments that are being left on your eye are probably polar in some form, which means they would be hydrophilic, which means that hydrophilic means water loving. So they probably have the pigments in regular mascara is liable to interact with water, just like alcohol and water can mix together. But you know, oil and water don't mix together. That's because oil is non-polar and water is polar. So they have like different ways that they want to interact with each other. So I suspect that waterproof mascara is some kind of oil-based, non-polar something that the pigments are not likely to interact with water, but that's also why they're harder to wash off. And you have to use soap or something that can interact with them. That is my theory. That's my chemistry off the cuff, but I don't know for sure. Interesting.
What do you think?
I don't know that I have a theory or whatever, but I was actually remembering as soon as reading this that my wife got a brand of waterproof mascara at some point that was like almost too good, and so then when she was trying to take it off, she was like, "Yeah, how do I get this off?" And she would get it sort of to like kind of come off, but it would end up kind of we would joke that she looked like a little bit of like raccoon eyes.
Yeah.
Because she would, like rub it and clean it off, but then there would be just a little bit of this like shadowy kind of residue around her eyes if she didn't kind of keep going again. But yeah, she's tried different ones. I think she probably has one she likes now because it's been a while since we've had that conversation. But it being like, whoa, this really is waterproof.
Yeah.
Even when I want to take it off, it's not coming off.
And there are oil-based cleansers that I'm like, how is this cleanse? What is it trying to cleanse? But it is very useful for that kind of makeup that is hard to get off with just water. Even with water and soap, it's like you get it dissolved in the oily cleanser first, and then you can wash it away with soap and water. I've noticed is a like approach I use often because it's like just the oily cleanser can't get it off, and just the soap, it's like the oily parts are too dug in there to where if you don't know the background of this, you can listen to our first ever episode about soap. But the soap molecules can't even interact with the oil because it's so caked on or something that then by loosening it up with the oil-based cleanser and then having the regular cleanser wash away the oil that is interacted with whatever you're trying to get off seems to be a good approach. And I used this when we were painting our house because we had an oil-based primer and it was so hard to get off. But then I got out my oil-based cleanser for makeup and I ran that all over my hands, and then my whole hands would get milky white with like, oh, the pigment is dissolved in this oil. And then I would wash the oil off with regular soap and water.
Nice.
So, and I similarly had a problem. Can I go on a little chemistry tangent here?
Why not?
Okay, great. So we're doing a little remodeling on our house, and the bathroom had a really bad leak when we bought it, the whole thing. You can listen to a community episode to learn more. But some of the the tiles they shipped us had tape on it, but it was really strong tape, and we had to take the sticky stuff off that it left behind.
Use like Goo Gone or something like that or whatever.
Well, I, of course, as a chemist, I'm like, well, it's either polar or it's not. And so I should be able to get this off. I tried mineral spirits, which is like non-polar oil, didn't work. I tried isopropyl alcohol, and what I noticed was with each of these, it would peel up some, but then there would be more residue left behind. And then you get the other one, and it would peel up the other residue, but then there was still some of the first left behind. And I think after removing this multiple times, I eventually used like a razor to scrape it off. I have a suspicion that there was like a polar part of the adhesive on one layer and then a non-polar layer.
Wow.
Because it was like I could use the one of the solvents to get the top layer off, and that was enough to where I could scrape the bottom layer off. But I couldn't just scrape. And I had to use it in that particular order. I couldn't use the other one first. It didn't do the same thing. It was like, what is the chemistry of what's happening here?
Yeah.
So those are all my thoughts.
Dang, interesting. Wow.
I don't think I realized this before, but I'm like constantly being like, what are the intermolecular forces behind what's happening here? And how can I leverage that to get to get what I want? So like use it for taking off waterproof mascara, used it for taking paint off my hands, and I used it for taking the adhesive off, but it sort of failed me on the adhesive one. That was frustrating. So.
Yeah. That's interesting. And it is weird because it's like, obviously whoever's making it adhesive is working pretty hard to figure out how can I make this work really well in the situation it's going to be in. And so they've got a totally different set of things they're thinking through, which is, I want this to be polar so that it's hard for, or I want there to be 2 layers, maybe polar and non-polar layers, so that it has a backup for if it gets a little bit wet or something like that. It's like it's just like, without being told what that is, you're just having to reverse engineer it, basically.
Yeah.
Which you can do, but requires some of the
Yeah.
Trial and error.
And I will say, they could have just taped it on the side that was going to be cemented down.
Yeah.
And not on the fancy polished finished side.
Right.
That was really where they got me.
Gotcha.
Do you have any other questions for me?
I don't. You have a question for you though.
Oh, that's right. Yes, my friend / sort of colleague / affiliate of the university, Dr. Diana Mason. She's I think I've mentioned her before on the podcast. She's a professor emeritus at UNT. So that means that she's retired, but she's like, still around. And she emailed and said, just listen to the episode y'all did on shooting stars. You mentioned that meteors might be bringing amino acids into the Earth's atmosphere and surmised about the origin. Please check out the Miller-Urey experiment. And I had heard of this, although initially when I didn't realize it was called that. We talked about how there is a theory that meteors are part of what brought amino acids into the Earth because we weren't confident it would have been made, from the ingredients that were already on Earth.
Mm-hmm.
But I had forgotten that there is an experiment, the Miller-Urey experiment, that recreated the early Earth atmosphere to see if it was possible that amino acids could form in that like primordial soup environment. And they did. And actually, when I went and looked this up after Dr. Mason emailed me, I found that there were some other experiments that weren't as well published or publicized out of that same lab where they one gave air flows and found that if you flowed air over this primordial soup mixture, it gave even more different organic compounds, more amino acids were formed. So yes, potentially amino acids were brought to Earth from meteors, but also potentially amino acids were made from the pre-existing molecules that were already in the Earth.
Dang.
In the Earth's atmosphere.
Interesting.
So very interesting. And she also gave me this tidbit, which I thought was fun. Tina May Winnie, I think is how you pronounce it, is a person an alumni from UNT, and they created an endowed scholarship for graduate students in education research that I received. And that person is related to Urey from the Miller-Urey experiment. So I got a scholarship from someone who's related to that person.
Wow.
Isn't that cool?
That's awesome.
And I just want to shout out that person because, boy, grad school is rough. And that scholarship really helped me survive.
Nice.
Like, quite literally helped me survive.
Literally.
Like, fed me. So.
There you go.
Yeah.
Wow.
So that's kind of a fun email that I wanted to share with y'all
That's
as
awesome.
well. But I think that's it. Do you have anything else for me? It's kind of a longer one, shorter, less questions, but more detailed explanations.
Yeah. That's all I got.
Awesome.
Want to wrap us up?
Yeah. Thanks for coming and asking questions.
Of course. Thanks for y'all sending them in. So like I said at the top of the episode, this is where those end up. So when you send them to us on our website at chemforyourlife.com, that's chemforyourlife.com, share thoughts, ideas, questions, follow-ups, whatever with us. Could be in this episode, could end up being a full episode on its own. Either way, we'd love to hear those questions. So please send them to us. If you'd like to help us keep our show going and contribute to cover the cost of making it, you can join our super cool Chem community of patrons on patreon.com/chemforyourlife. That's where Ash asked their question about mosquito patches. And so we'd love to, interact with you over there. And you can keep the show going, keep it free for everybody else. And we're grateful for our community. You can also support the show by grabbing some merch on our website at chemforyourlife.com/store. You can also support the show by subscribing to your favorite podcast app, rating, writing a review on Apple Podcasts or Spotify or whatever app you use, subscribing on YouTube, leaving a comment over there like our silicone, siloxanes, silo, how's it again?
I think it's siloxanes.
Okay, there we go.
Siloxanes.
Comments, saying hello over there, those things, commenting, subscribing, all that kind of stuff just helps other people find the show and helps us explain the chemistry of their everyday life to them, which is the whole point. So thanks for doing that.
This episode of Chemistry for Your Life was created by Melissa Collini and J.M. Robinson. J.M. Robinson is our producer, and if you'd like to learn more about the references that we used in this episode, you can check out our show notes or our website where they are linked. And we always like to thank every single person who contributes to our community and helps keep the show going by name. So we want to thank Hunter, Chris, Claire, Stephen, Timothy, Katrina, Scott, Vince, Kyle, Bree, Brian, Latila, Rachel, Elizabeth, John, Jesse, Doreen, Heather, Ash. Thanks for your question, Ash. Sarah, Avishai, Chelsea, Christina, Jacob, Venus, Suzanne, Erica, Cullen, Autoclave, Julie, Justine, Amanda, Summer, and Dog Day Dan. Yay, chemistry!
Yay, chemistry!